Welcome! This video analyzes the response of an RC circuit to a pulse train input voltage signal. The blue VN voltage input signal is a pulse train with a pulse width of 1 microsecond. At 0, 2, and 4 microseconds, there is a steep rising edge on the VN input voltage. At 1, 3, and 5 microseconds, there is a falling edge in the VN pulse train signal. For this circuit, with a 20 nanofarad capacitor, what values of output voltage, vout, do we expect to see at the three marked points in time? 1 microsecond, 2 microseconds, and 3 microseconds. We'll work through the calculation equations in this three-part exercise and then compare the calculated results to LTspice simulation results. The value of vout at 1 microsecond is the result of the step response starting at time t equals 0. With the output capacitor voltage equal to 0, when the step is applied, the VN voltage gets initially applied only across the resistor because the capacitor voltage cannot change instantaneously. We can use the step response equation to describe the red vout rising exponential.
For more technical background and insight on step response and natural response, please see this book, First and Second Order Circuits and Equations, available from John Wiley Sons.
To calculate the voltage vout at 1 microsecond, substitute circuit element values into the step response equation. 1 microsecond is the time, 20 ohms is the resistance, and 20 nanofarads is the capacitance.
20 times 20 is 400. Gather the 400 below the 1 from 1 microsecond. Gather the 10 to the minus 6 term from microseconds with the 10 to the minus 9 term from nanofarads. 1 divided by 400 is 0.0025, and 10 to the minus 6 divided by 10 to the minus 9 equals 10 to the plus 3, or 1,000. The exponential term reduces to e to the minus 2.5, which equals 0.083. 1 minus 0.083 equals 917 millivolts for V of vout at 1 microsecond, having started from 0 volts at time 0.
917 millivolts is what we expect to see for vout at 1 microsecond, completing the first part of the exercise. Continuing the exercise at 2 microseconds, what do we expect the value of vout to be? And how do we calculate this value? The value at 2 microseconds results from exponential decay starting at 1 microsecond in time. The exponentially decreasing red vout signal across the output capacitor, responding to the falling edges of the blue input voltage signal VN, looks like a set of natural responses. With 10 nanofarads of capacitance, vout gets very close to the values of VN before the rising and falling edges of VN. But the signals don't match the formal description of natural response. There isn't an ideal initial condition voltage on the output capacitor with no other inputs. How can we apply a natural response equation to this situation? With 20 nanofarads in this pulse train response example, the red output signal via Vout at 1, 3, and 5 microseconds is smaller than the input voltage via Vin. This means that the decreasing exponential decay of via Vout starts below the 1 volt value of via Vin. We can't use via Vin in the natural response equation for this application, but we can use the value of the output voltage via Vout at the time of the falling edge as the initial condition term. Call the maximum value of the output voltage via Vout at 1, 3, and 5 microseconds via Vout peak. As shown here, we use via Vout peak in the natural response equation in place of the initial condition in the formal natural response equation. The high value of via Vout at 1 microsecond was 917 millivolts. For the quote via Vin unquote term, or rather, the via Vout peak term, in this natural response equation, we will use 917 millivolts for the calculation of via Vout at 2 microseconds. The exponential term of the natural response equation is the same as it was previously in the step response equation. The time duration is 1 microsecond. The resistance and capacitance are both the same here as they were before.
The exponential term equals 0.083. 917 millivolts, the value for via Vout peak, times 0.083, the exponential term, equals 76 millivolts.
76 millivolts is the value of the red via Vout voltage that we expect to see at 2 microseconds time. This completes the second part of the exercise. For the third and final part of the exercise, what value of the via Vout capacitor voltage do we expect to see at 3 microseconds, and why? At 2 microseconds, the value of via Vout is 76 millivolts, when the via Vin 1 volt step gets applied across the series connection of the resistor and the capacitor. In the step response equation for this series RC circuit, the via Vin term is the voltage across the resistor at time 0. More generally, by KVL, the resistor voltage is via Vin minus via Vout. But in zero-state response, the capacitor output voltage via Vout equals 0 at time 0, and all of the via Vin voltage drops across the resistor at the instant of the rising step voltage. This is because the voltage across the capacitor cannot change instantaneously. At 2 microseconds, via Vout does not equal 0. To calculate the exponential response from 2 microseconds to 3 microseconds, we need to adjust the via Vin term in the step response equation. Call the low value of the output voltage via Vout at 2 and 4 microseconds via Vout low. As shown here, use the term via Vin minus via Vout low in the step response equation in place of the via Vin voltage in the standard step response equation. The quantity V of Vin minus V of Vout low is the voltage across the resistor, and now we can plug in values to solve for V of Vout at 3 microseconds. When the step response starts at 2 microseconds, the voltage across the resistor is 1 volt minus 76 millivolts, or 924 millivolts. 76 millivolts is the voltage across the capacitor at 2 microseconds. 924 millivolts, or 0.924 volts, is the value we need to use for the quantity V of Vn minus V of Vout low in our modified step response equation. 924 millivolts multiplied by 0.917 equals 847 millivolts. The output voltage increase going beyond the 76 millivolts starting point voltage across the capacitor. Now add 847 millivolts to 76 millivolts to get 923 millivolts, the value of V of Vout that we expect to see at 3 microseconds. The sum of 76 millivolts and 847 millivolts is shown vertically on the graph right by the 2 microsecond rising edge. Let's now check our calculated capacitor output voltage values against a simulation with LTspice. The circuit has no delay time before the start of the pulse at time 0. The rise and fall times of the input signal are 1 nanosecond. Click on the tab to go to the results. To get a marker called an attached cursor on the plot, go to the signal label at the top of the graph and click left mouse button. A crosshair appears on the screen. Pull the readout box up into view. Point the mouse at the crosshair. When you move the mouse right to the crosshair, you see a number, 1 for the first attached cursor. Holding down the left mouse button, you can drag this number along the curve to mark and measure any point you wish. Let's zoom in. When we zoom in, we can see the marker shows a value very close to the 917 millivolts that we calculated with equations. Now move the cursor down to the 2 microsecond low value of V of Vout. First zoom out. Slide the cursor along to the right. The attached cursor follows the curve. We can see from the readout on the right that we're very close to the 76 millivolts that we had calculated. To get a second marker, a second attached cursor, go back to the top of the graph and click again on the V of Vout label. We get a second crosshair. Move the mouse to the new crosshair on the signal plot. We see a number 2. Drag this marker along the curve to 3 microseconds. We see that the vertical value is very close to the 923 millivolts, like we calculated with the equation. Here we can also see the vertical difference between the two markers. The value is close to the 847 millivolts that we calculated. Thank you for watching and learning with us.